Let's now consider a slightly more complicated linear map. Okay, this is a linear map between R2, the space of two tall vectors, and the space R3 of vectors with three components, defined by the mapping shown here. Now let's just take a few examples to consider a few examples of what this map actually means. Let's say that we have 1, 1. What does that go to? Well, 1, 1 is going to get mapped to 1, 1, because x and y are still 1, but then that's going to be minus 2. Okay, and then say another example would be, say, 3, 2, getting mapped to 3, 2, minus 2 plus minus 3 is minus 5. Okay, those are just a few examples to make things concrete. Now, let's consider whether it's a map. So we need to show that for arbitrary vectors v1 and v2 in the domain, that the images are also equal, that f of v1 equals f of v2. So to prove a conditional, let's start by assuming the premise for arbitrary or typical v1 and v2. So we'll assume that v1 equals v2. Now we need to show that this is true. Okay, well, what does this actually mean in terms of this space? What this means is that we're assuming that x1, y1 equals x2, y2. Well, let's consider what f of v1 is. F of v1 equals x1, y1 minus x1 minus y1. Well, since x1 by this equation here, by the top one, x1 equals x2 and y1 equals y2, we know that this is equal to x2 and y2 and minus x2 minus y2, because x1 has to equal x2 and y1 has to equal y2. But this is just the image of x2, y2, that is f of that, which is equal to f of v2, showing that this is a map. Okay, let's consider whether the map is linear. Well, to do that, we need to choose, again, for any vectors v1 and v2, we have to look at what the image of x1, y1 plus x2, y2, and our rule tells us how to send one vector. So we first have to perform the vector sum to get f of x1 plus x2, y1 plus y2 is the two components. Then we can apply the rule and see that that's equal to x1 plus x2, y1 plus y2, and then minus x1 minus x2 minus y1 minus y2. And the idea now is to separate the ones on the left and the twos on the right. So we'll have x1 plus x2, y1 plus y2, and then over here minus x1 minus y1 plus minus x2 minus y2. Okay, and that's going to be equal to x1, y1 minus x1 minus y1 plus x2, y2 minus x2 minus y2. And we can see that this first vector is just the image of, it's going to be f of v1 here, and then x2, y2 minus x2 minus y2. The second vector is the image of v2. So this first property holds true, and we have to check one more property, the second property, which is a little simpler, but we have to still go and say, let's look for the image of an arbitrary number r times xy. Well, we multiply in the r to get one vector, so we'll know how to implement the map. And then this is equal to rx, ry, minus rx minus ry. And then we can use the property of vector scalar multiplication to factor out the r. That's going to be r times xy minus x minus y, which equals r times f of v. So indeed, it's a linear function. Okay, now let's consider, is it one-to-one? Well, let's choose two arbitrary vectors, v1 and v2, as shown here with components x1, y1 and x2, y2. And we're going to assume the premise that the images of v1 and v2 are equal, and we want to show that v1 and v2 are equal on that basis. Okay, well, this vector equality implies that the corresponding components are equal. So x1 equals x2 and y1 equals y2. And that directly means that v1, which equals x1, y1, which equals x2, y2, equals v2. So indeed, it's one-to-one. And we want to do the same thing and look, is this map onto? Well, that means we have to choose an arbitrary w, okay, that is a member of the codomain. That's the member of R3. So we can choose. Now, it's going to turn out that this is, looking ahead, we can see that the map makes a correspondence between x, y, and z, the last component. So it's not going to be onto, so we just need to look for a counterexample. So this is the counterexample we're choosing. So we're not going to actually prove this. We're going to show it's not true, in fact. So we have to show now that for this, there is no, if it is an image of some vector, of an arbitrary vector, we're going to get a contradiction. Okay, so suppose this is an image of a vector with components x, y, minus x minus y. That is, that it's the image of some vector v. Well, this implies that x equals 1 on the top row, that the second component's y equals 0, but that means from the last row that 0, which equals minus x minus y, because x is 1 and y is 0, these imply that 0 equals minus 1. Therefore, the map is not onto, because it's not possible to find a map, a vector v that maps to this one here.